Okay, hello everyone, and welcome to this week's SEDS Online webinar. My name is Mariano Ramirez, and I'm going to moderate today's talk. Before we get started with today's webinar, we would like to thank our sponsorship from the International Association of Sedimentologists, which allow us to offer all of these resources free of charge. Make sure and check out our website for more information on upcoming events and meetings and to see everything available for our community. Also, I would like to remember you that we are still looking for presenters for our 4th SEDS Online student webinar, which will be on Wednesday, the 1st of December. And the topic will be exploring sediment transport dynamic from source to sinks. Please also remember that the proposals should be submitted by the 27th of October. So today's lecture is by Marta Cosma from the Institute of Shale Sciences and Earth Resources of the National Research Council of Italy. Marta received his bachelor degree and her PhD from the Department of Shale Sciences in the Università di Padova in Italy. Her current research focuses on tidal processes on both modern and ancient environments. And today she's going to talk to us about 3D architecture and a long bend sediment distribution on hypertidal point bar in Mont-Saint-Michel Bay in France. So Marta, I'm going to let you to share your screen.
Thank you.
And after that, the stage is yours.
Okay. Can you see my screen now, right?
Yes.
Perfect. So I'm really glad to be here today. It was really unexpected to be invited to this kind of talk. So first of all, I have to say a huge thank you to SEDS Online and also to my supervisor and my co-supervisor, Massimiliano Ghinassi and Andrea Del Paos, which helped me during my PhD. And also, I have to say a big thank you to my French colleague from the Geoscience Rennes, the University of Rennes in France, Dimitri Lag, Jérôme Leroux, and Baptiste Feldman, which made this work possible. So today I'm showing you the 3D architecture and the long bend sediment distribution of the hypertidal point bar in Mont-Saint-Michel Bay in France, using both that was analyzed through aerial photo, Lidar data, and sedimentary-core data. So this is a recently published paper on that here in Sedimentology. And I also going to show you some data from the PhD thesis of Jérôme Leroux, which collect a lot of Lidar data that I'm using in this study. So tidal meandering channel are ubiquitous feature of the tidal environment. They are fundamental pathway for water, sediment, and nutrient distribution, and they control the ecomorphodynamic evolution and sedimentary architecture of coastal plains. The tidal meandering show really complex hydrodynamic. They are characterized by bidirectional flow, which cause a short-term variation of channel discharge and velocity. They are characterized by the asymmetry and the hysteresis of the tidal flow cause the inequalities of the ebb and flood magnitude and the flow periods, and the mutually evasive nature of the flood currents cause the offset of the highest velocity and the secondary recirculation within the meander. Therefore, they are characterized by really complex hydrodynamic, which can influence the development and the processes that are occurring in tidal point bars. Tidal point bars develop from the migration of tidal meanders. And they are mainly studied in the vertical framework. Tidal point bars are known to develop inclined heterolithic stratification, and they are usually fine grain. They usually consist of fine grain sediment. They show fining upward trend, and with bearing the tidal signature in the upper portion of the tidal point bar, with tidal RHYTHMITES in the upper point bar. And here's an example from the Gonso Bay by Choi, in which he showed that tidal RHYTHMITES are developing between the mean sea level and the mean high water level. Therefore, as I said before, tidal point bars are mainly studied in a vertical framework. However, a lot less attention has been given to the along band distribution of sedimentary facies, which can be as much important as the vertical trends, considering the complex hydrodynamic of the tidal flow within a meander that I showed you before. Therefore, with the help of a series of aerial photos and high-resolution 3D Lidar surveys and sedimentary core, we reconstruct the evolution of the tidal meander and the 3D architecture of tidal point bar from the long term to the short term, so from the decennial time scale to the daily time scale, particularly focusing on the along band distribution of sediments and tidal signature. So this is the summary of my presentation. I'm going to give you a brief introduction of the Bay of Mont-Saint-Michel and the study sites. And then I will pass through the multi-annual evolution of tidal channel made using essentially aerial photos. And then I will show you the early evolution of the study tidal meander and the 3D architecture of the point bar deposits using Lidar surveys and sedimentary core. And then I will give you some information about the daily evolution of the tidal meander with the erosion and accretion patterns, which is it's part of the PhD thesis of Jérôme, my colleague. So the Bay of Mont-Saint-Michel and the study site. The Bay of Mont-Saint-Michel is a wide and shallow basin that dipping toward the northwest, and it shows three main sub-environments: the shelter embayment, which is characterized by tidal flats in the southwest of the bay, a narrow and wave-dominated barrier system in the northwest, and huge estuarine domain in the southeastern portion of the bay. Except for the wave-dominated barrier, the bay is actually quite protected from the wave action by the Cotentin Peninsula and an archipelago, the Chaucy highlands that are occurring up here. Furthermore, there are three rivers that flow within the bay: the Sea, the Sélune, and the Couesnon, which show a mean annual discharge. Each one of them show a mean annual discharge of 8 to 10 cubic meter per second. therefore, which is actually negligible. Therefore, the estuary domain in here is characterized by the tidal dominance. So this is a tide-dominated estuary in system, which show a semi-diurnal hypertidal regime, which has tidal amplitude that can be up to 15.3 meter for spring tides, and the tidal amplitude are quite they show a really huge variation. In this graph here, it's quite small, but I hope you can see that here you have the high tide elevation for a period of 4 years, sorry. And you can see here the variation of the high tide for nip and spring periods for the annual tidal cycle, and also for the long, like 4-year higher order 4-year tidal cyclicity. On the bay, the tide velocity on the tidal flats ranges between 1 meter in the outer bay, and they go down to 0.3 to 0.7 meter per second in the inner bay, with the maximum flow velocity occurring on the tidal channels, which can be up to 2.5 meter per second. The bay show the decrease in the mean grain size on the bottom of the bay, which toward the estuarine domain. So the in the outer portion of the bay, you can find medium to coarse gravel, while toward the inner portion of the bay, you will have just silt and sand. There is a major marine sedimentary input, whereas the sedimentary input from the river is negligible. Due to the natural infilling of the bay, and also because of the human intervention, there was a huge progradation of the salt marshes in the estuarine domain, and particularly near the Mont-Saint-Michel Bay here. What happened is that the reclamation of land and the construction of dam inhibits the natural migration of the different rivers flowing in the bay, which are not more able to transport the sediments occurring here toward the outer bank. And therefore, there is a major accretion of salt marshes in the last 50 days, which cause which need therefore to restore the maritime character of the Mont-Saint-Michel Bay, which is the Mont-Saint-Michel, sorry, area, which is particularly famous and a touristic attraction. They need to do a lot of engineering works to restore the maritime character of this area. So the study site you can see here is really located in the Estuarine domain, and really near the medieval bay, and not far from the river, the Cruzenon River mouth. Here you can see an example. You can see where the channel is with respect to the abbey. The channel is located in the upper intertidal zone, and it cuts through salt marshes. Here you can see a Lidar dam of the 2017, which show the meander, which has a radius of curvature of about 125 meters and a channel depth at the bank full scale, which has the channel depth is 3 meters deep at the bank full stage. In this area, there is a clear vegetation zonation, which is typical of the Mont-Saint-Michel area, with high marshes located over 7 meters above sea level, middle marshes that occur between 7 meters and 6.2 meters above mean sea level, and low marshes which occur between 6.2 and 4.5 meters above sea level. And you can see here that the low marshes arrive at the apex zone here in the point bar. So just to give you an idea of the system, you can see here that between 2009 and 2013, just only the 4% of the tides reaching the study area flooded the high marsh, and these are called overmarsh tide, whereas the middle marsh was flooded only by the 25% of the tides, and of course here the channel Talweg is flooded of about more than 70% of the tides. So here you are looking at the point bar at low tides with the outer bank, here the Talweg, the bar slope, and the bar top with the finer vegetation on them. And you can see here a cross section of the point bar along the channel along the axis of the channel. You can see that we are in the upper tidal zone and near the mean high water level. Here again, you can see the high tide elevation with the for a period of 2 months, which show the differences between the spring high tides and the neap high tides. Looking at the relative elevation of the channel with respect to the tide elevation, you can see that the channel empties out at each time, so at each tide, so 2 times per day. And here you see the situation at low tides. Just to give you an idea of the sediments we have in this point bar and in this meander, they show quite a classical feature for tidal point bars. So there is a finding upward trend from the Talweg zone, which show very fine to fine massive sand with mud clasts and shell, and they finding upward to laminated mud with very fine sand, which toward the bar top. The plain bed and cross ripple are quite current ripple are quite common, and they show a tidal rhythmicity. Furthermore, in the bar top, you will see oxidation and mud cracks related to subaerial erosion of this zone, and also roots related to the pioneer vegetation. Along the bar slope, there are also occurring scour and slumps, and also some kind of reels which transport sediments toward the Talvik zone. And this was just to give you an idea of the study site. So now I'm showing you a multi-annual evolution of the tidal channel, which was studied by using aerial photos. So here you can see the study channel in the 1997. You can see these are the salt marshes. The channel was quite wide and showed the classical funneling related to the classical tidal feature. And the channel here show quite a low sinuosity. So in time, what happened is that there is a general seaward migration of the tidal channel Talvik, but in some places like these, which is our study cases, there is also a landward shift of the channel in time. So there is a seaward and landward shift of the channel, and there is also an expansion of the salt marshes. Here again, you can see the time passes. There is a seaward migration of the channel and the expansion of the salt marshes. These occur until vegetation starts to develop on bar top in 2010. After these, here, there is generally northward expansion, you can see here, of the channel, and a further development of the salt marshes toward north. So again, what happened during the last 20 years, there is a huge expansion of salt marshes, and the channel migrated before 2010, migrated just in a overall seaward migration, but with back and forward from landward to seaward migration, whereas when salt marshes develop, the meanders start to increase its sinuosity and to expand toward the north. So there's probably what happened here is that with the salt marsh development and the colonization of the bar top, the point bar is more resistant to erosion, and therefore these hindered the seaward migration and promote the expansion of the meander. There is actually another possible influencing factor which can be related to the higher order tidal cyclicity. In fact, in the area, there is a paper by Levoy in 2017 on the Mont-Saint-Michel Bay, which correlated the back and forward the movement of the Sea, Saloon, and Cosenon River to the 18.6-year lunar nodal tidal cycle. However, we do not have the data for our study case to see if this is the case also for our tidal meanders. But for sure, there's intertwined relation and feedbacks between the salt marsh evolution and the tidal channel evolution. Looking a little bit closer to our study meander, we can see here the expansion between July 2010 and July 2013, the retreat of the outer bank toward north of about 15 to 20 meters, and the progressive colonization of the pioneer vegetation in this period. And this is also related to the progressive accretion of point bar deposits, which go toward the north and toward the northwest. And looking at the cross-section, we can see almost the same thing. So between 2010 to 2017, we can see that there is an accretion of the point bar deposits and then lateral migration. So there is, if you look at the point bar rink, which is actually the breaking slope between bar top deposits, flat bar top deposit and inclined bar slope deposits, we can see that there is a general ascending trajectory of the point bar rink, and there's a general descending trajectory of the channel Talbot, even though there is quite dynamic evolution with a rising trajectory and then descending trajectory. So the evolution of the point bar rink and the channel Talbot allow us to recognize that there's generally an increase in point bar thickness and accretion of the point bar. So if you are interested in the accretion and lateral migration of, in the relation between accretion and lateral migration on point bar deposits, there are a few references here with few recently published article of my research group. So related to the overall, to the multi-annual time scale, we saw that the tidal channel show an overall seaward migration with the difference with landward and seaward migration and a low sinuosity before the 2010 with the salt marsh expansion, and more expansional behavior after the 2010 because of the progressive colonization of the bar top by vegetation, which accrete toward the north-northwest. And this is again related to the influence of the vegetation on the long term and possible the influence on the higher order tidal cyclicality. Now going to the early evolution of the tidal channel and the 3D architecture of point bar deposits. So this was made combining Lidar data with sedimentary-core data. In particular, we have from the Leroux work in he collected a lot of terrestrial laser scanner high resolution surveys. In particularly, there are 36 TLS survey between 2009 and 2013, and we also have 7 long-range Lidar surveys available. So I will use some of the TLS data for the daily analysis, which I'm going to show you in a few moments, which are related to the PhD of Leroux. But for the yearly analysis that I'm going to show you now, we selected 12 terrestrial LiDAR surveys spanning between 2012 and 2013, and we also have one long-range LiDAR survey in 2017. We used these surveys here in 2012 because they are quite distributed along the year. So LiDAR data were processed in Cloud Compare, an open source software for the processing and editing of point clouds. And there was a pre-processing of the LiDAR survey to remove vegetation and to reconstruct the channel talweg where at low tides, where water occurred at low tides in here. So we, using a particularly plugin in Cloud Compare, we were able to reconstruct and to interpolate the channel talweg. So all these different LiDAR surveys were used in with the help of a Python script, were used to create the synthetic stratigraphy of the bar. Essentially, it means that each survey was clipped whenever one of the following surveys show lower elevation. This means that this area here were affected by erosion. So in this way, we identify where erosion occurs, but more importantly, we can identify the package of sediments deposited in 2012, which is actually preserved in the bar. And also, we can understand where preserved deposits accumulated between the different surveys, which are called internal increments. So using the synthetic stratigraphy, we can actually understand which deposits are preserved in the stratigraphy. Furthermore, we collect 7 cores along the band. We cut them longitude with an auger corner. Here you can see my supervisor doing his job and helped me in this really tough work. So we use a auger core that allows to avoid compaction of sediments. The sediment were then cut longitudinally and photographed and logged, and we perform a quantitative patches analysis at the centimeter scale. In particularly, we classify each centimeter considering the percentage of sand and mud. Therefore, we have 5 different classes. The dark orange is 100% of sand, whereas the dark gray color is 100% of mud. And there are the other classes are just in between. And we also analyze the tidal signature. So we define whether or not the nip spring tidal cycle were complete, absent, or incomplete. So these show the thickness of the sediments accreted along the bar between March and November 2012, which are actually preserved in the stratigraphy. And we call these the 2012 accretionary package. The accretionary package has an arcuate shape with maximum thickness preserved in the apex zone. These show the thickness of the deposits preserved between the different surveys, so the different internal increments. And you can see that there is a quite alternating behavior on the deposition. So some of them show deposits both in the apex, in the seaward, and in the landward zone. Some others show only in the landward zone, only toward the seaward part of the point bar, and some other only toward the landward part. So there is quite an alternating behavior of the preserved deposits. Looking at the actual cross-section here, you can see that the accretionary package pinches out both toward the bar top and toward the channel tidal, with the thickest deposits recorded on the bar slope. Along the band, the thickest deposits and the maximum number of preserved internal increments are located in the apex zone and just landward of it, while the thinner deposits and the minimum number of preserved internal increments are preserved in the seaward side. So these are all the cores collected along the bar with the different elevation with respect to the mean sea level. This is just to give you an idea about how much these kind of deposits were flooded by the tides. So the flooding frequencies calculated in 2012 show that only the 3% of the tides in the study period flooded the high marsh, so the elevation over 7 meters above mean sea level. Whereas in this elevation here, we saw that we see that 53% of the tide can reach the 5 meters, and at this elevation, one nip spring cycle consists in mean of 15 tides out of the 28 possible in a semi-diurnal tidal regime. Whereas at the 4.1 meter, which is a little bit higher than the channel tide, we can see that the tide reaches this zone are the 76%, and in here the nip spring cycle consists of 22 tides. And these, I will go back to these in few slides, is really affecting the kind of tidal arithmetics we can register in this area. So we are now looking at the sediment distribution along the bar. So here you can see the internal increments that are, and the maximum thickness of the accretionary package in the apex zone and landward zone, and again the minimum preserved interval in the seaward side. And here you can see the different cores. with the percentages of sand and mud. You can see here that there is a clear grain size trend. In particular, the seaward side consists coarser grain size, so sand is more abundant in the seaward side, whereas thinner deposits, finer deposits, so muddy deposits are more abundant in the apex zone and just landward of it. The thinner deposits combined with coarser sediments in the seaward side suggest that this portion of the point bar is more prone to erosional and bypass processes, whereas the apex zone and the landward side of the point bar is more prone to depositional processes. So these are how tidal rhythmites look like in the study bar. So one tidal cycle is registered in a couplet of sand and mud lamina because we are in the upper-intertidal zone and the low tide do not affect this area. The nip and spring sequence is recorded by the thickening and thinning of the sandy and mud couplets, which reflect the progressive increase and decrease in the energy of the tide. We have from 6 to 12 tidal cycle recorded in a nip spring sequence, usually out of the 28 possible in a semi-diurnal tidal regime. And these numbers it is quite common in the upper intertidal zone, and there are quite a lot of work by Tessier in the Mont-Saint-Michel, which agree actually with what we found in this area. So the complete sequence, nip spring sequence, can have different thickness ranging from 7 centimeter to few centimeter, which show thinner couplets of sandy and mud. So we can have just complete sequence, nip and spring sequences, but we can also record just incomplete sequences, or we can have no rhythmicity at all. It is interesting to note, I was showing you the flooding frequency of the tidal meander of the study zone, and it is interesting to note that the registered tidal cycle on the nip and spring sequence are just like a half of the tides that are reaching the study site during a nip spring cycle. Okay. And these show the tidal rhythmites along the point bar. And first of all, it emerges that tidal rhythmites are not so common. The 60% of thickness do not, and higher percentages, do not show rhythmicity at all. Furthermore, preservation of the tidal rhythmites is higher in the apex zone and just landward of it, and they are really less. There are really few tidal rhythmites recorded in the seaward side. Last but not the least, tidal rhythmites occur in protected areas, such these local scour here. You have tidal rhythmites on both core 3 and 4. And they are preserved in the lower point bar deposits. So concluding the analysis at the early time scale, this was one of the first attempts to combine sedimentary core to Lidar data and the synthetic stratigraphy in a real case example, which help us to reconstruct the 3D architecture of the tidal point bar. The accretionary package show really thin, show an increase of thickness and a number of preserved interval and abundance of tidal rhythmites and mud in the apex zone and just landward. Whereas in the seaward side, there's thinner deposits and less tidal rhythmites and mud. And this is related probably to the more frequent erosion and bypass processes toward the seaward side, while more depositional processes occur in the apex and landward side. After the section on the daily time scale, I will go back and I will show you the positional model for this tidal meander. And again, I repeat that the nib spring sequence are rare. Tidal rhythmicity in these point bar deposits are rare, and only half of the tides that reach this area are recorded in the stratigraphy in the point bar. So as I was saying before, now I'm going to show you the daily evolution of the tidal meander with showing you the erosion and accretion pattern and the controlling factors of this pattern. This is actually part of the Jérôme Leroux PhD thesis. So again, he uses Lidar data, the TLS data from 2009 to 2013, and he did first processing of the data with the classification of the vegetation using the Canupo plugin, always in Cloud Compare, which allows him to define where vegetation occurs and to in order to delete these points from the Lidar data. Then he did this both in the point bar and in the outer bank here. He used the ground, only the ground points were used then to the analysis on the daily topographic changes. He used dam of distance of consecutive days using the M3C2 plugin, always in Cloud Compare. M3C2 use directly the point cloud without any kind of interpolation methods, and therefore the minimum surface change detectable at the 95% confidence level is about 5 millimeters. So there's a really high resolution and precision on these data. So he looked then at the daily topographic change of these 3 zones. He called the inner bar all the points that are higher than 5 meters above the sea level, whereas the channel are related to points which are below 5 meters above mean sea level. And then he analyzed the outer band. Here you can see he uses 2 consecutive survey, and he analyzed the distance for the inner bar and the channel, mainly in a vertical direction, and he set the maximum distance between the 2 of about 20 centimeters, which is definitely a lot more higher than what actually are the accretion. But so he analyzed the vertical accretion in the inner bar and in the channel, whereas in the outer bank, of course, it is more important to look at the lateral variation on the position of the outer bank with the maximum displacement of 20 meters. And here there are some results from his thesis showing the rates of the topographic changes for the different area of the point bar. How to read these graphs? So here you can see there the topographic changes positive in meter per tide. So the positive number means that there is accretion, whereas negative number means that there is erosion, and they are correlated to the mean high water level. The graph, the gray line here show the elevation of the high marsh, which essentially discriminate between overmarsh tide and undermarsh tide. So how to read this data? So tide that show mean high water level will show a mean topographic change, in this case for 6.5 tide, mean high water tide, that there will be like in mean an accretion of about a few millimeters with the maximum accretion of the scale of the centimeter, and an erosion which is quite negligible. Whereas these graph here show the fraction of the surface that show a significant change in accretion with respect to the mean high water level. So I'm now going through all these different sections, the different area of the tidal meander, and I just want to show you that that there is a difference in the scale. So minimum and maximum accretion for the inner bar are like 5 centimeters, whereas for the channel topographic changes, they would be like 10 centimeters, and for the outer bank, they ranges between plus 50 to minus 2. So the inner bar, there is an overall accretion. Overall, the accretion is higher than the erosion, and this is in the scale of the millimeter and the centimeter for each tide. However, there is a really huge variability. You can see here the mean in the inner bar is usually positive, so there is accretion, And there is a really huge increase in the maximum accretion and in the erosion with the high water level. The accretion show a quite linear increase, whereas the erosion is quite stochastic. And also the variation, the surface affected by accretion is much higher than the surface affected by erosion. So there is a really huge variability in these patterns. And we can understand why, looking at the plan view of the study meander. Here you can see, I hope you can understand, this is the channel, the outer bank. This is the salt marshes, the pioneer vegetation, and the inner bar, so it is located here, and the floods come from here. So this is zoom in here, and you can see that that accretion is higher in the shadow zone behind the vegetation patches, and the flood is coming from here. So the accretion is really dependent on the shadow zone of the flood tides. And furthermore, there are seasonal variation of the vegetation patches. Therefore, really huge vegetation patches are developed in October, and therefore there's a little bit more accretion in this period. Whereas when vegetation are really small, accretion is lower. So therefore, overall, the inner bar is influenced by vegetation and the flood flow. The channel show the graph here show that accretion and erosion are quite similar to the inner bar, but they can be higher, up to 10 to 25 centimeters per tide, and there is a slight decrease in the mean accretion with the mean high water level. And again, the surface affected by accretion is higher than the surface affected by erosion. Looking at the plan for view, here you are looking at the accretion and erosion pattern of the three highest overmarsh tides in the study period. So between 2009 and 2013, they show a really peculiar pattern with erosion in the landward zone and accretion in the seaward side. Furthermore, there's also erosion also toward the seaward side here. Just to remember, these overmarsh tides represent only the 4% of the tides. And this peculiar pattern is really due to the flow pattern of the ebb and flood tides. So Jerome did also some hydrologic analysis, hydrosedimentary hydrologic analysis, and you can see that for undermarsh tides, there is velocity quite similar between the ebb and flood tides, whereas there is a huge dominance of the ebb flow for overmarsh tide. Looking at the flow pattern here, we can see that the flood coming from the west, it generally overtops the low marsh and the inner bar, and then go toward the outer bank toward the landward side. Whereas the channel, the ebb flow goes along the channel and recording the highest velocity toward the outer bank. So this kind of pattern is really related to the erosion during the ebb flow, and which then goes toward the outer bank. And this kind of deposition is whether related to the flood flow or also to the development of some kind of recirculation zone and low energy zone with dumping of sediments during the ebb flow. So this is really peculiar pattern, but again, this is occurring just really few times over the study period. So the depositional pattern change with the lower high water level. Here you can see again the overmarsh tide in here between different days in September, and just the day before, when undermarsh tide occur, we have a really depositional pattern in the apex zone and toward the landward part of the meander. And so with the lower high water level, these must be like a really important process, which explain, if you remember the early evolution of the meander, it explained the overall accretion in higher in the apex zone and in the landward side. The outer bank accretion is a lot less than erosion. You can see that the mean really drops down with the higher water level, and with the maximum erosion of the outer bank up to 2 meters for a single tide. And again, the surface affected by erosion in this case is much higher than the one affected by accretion, and it definitely increases a lot with the increase of the high water level. Here you can see that the accretion can be really looked locally in the outer bank, and they can be a little bit more diffuse. And this is again related to the very flow pattern of the ebb flow. So the outer bank is definitely influenced by the overmarsh tide, so the higher tide during the ebb flow. So summing up the daily time scale variation, there's generally a really high variability of the rates of the topographic changes, with the inner bay that is mostly influenced by vegetation and flood flow, the channel that has extremely complex pattern that are influenced by the ebb and flood flow pattern within the meander, with huge variation for undermarsh and overmarsh tides, whereas the outer bank dynamics is determined by the ebb flow during the overmarch tides. So I'm going to the conclusion. And so we use aerial photos and Lidar data to define the evolution of the study channel from the decennial to the tidal event timescale. We reconstruct the yearly 3D architecture of the point bar, which was achieved through the synthetic stratigraphy and core data. And this was one of the first attempts to combine this data to obtain the 3D architecture of the point bar. The long-term tidal channel evolution, that there is an, as you can see here, there's an overall seaward migration of the tidal channel with a complex behavior with the back and forward migration when the channel show low sinuosity, which is influenced by the progressive colonization of the point bar top by pioneer vegetation that leads to an expansional behavior of the tidal meander. In the yearly dynamic of the tidal meander, show that the long band distribution of sediments and tidal RHYTHMITES is strongly controlled by flood and ebb flow patterns. In particular, the flood flow coming from the west cause erosion and erosion of the most seaward part of the bar, and deposition here in the inner bar and in the apex zone, and just landward of it. Whereas the channel, whereas the ebb flow going along the channel causes during the overmarch tide cause erosion along the landward side and a lot of deposition for development of a low energy zone in the seaward side, and during high tide, during undermarch tide, there's a usually overall deposition on the apex zone and landward side. And this is actually recorded in the stratigraphy of the point bar, which show thinner deposits and abundance of coarse sediments in the seaward side, whereas a lot more thickest deposits, more a higher number of preserved interval, abundance of tidal RHYTHMITES and mud in the apex zone and just landward of it. And again, the daily topographic change of the tidal meander, as I was saying before, show that this portion of the bar is definitely influenced by the flood flow and by the vegetation occurring in here, whereas the channel accretion show a really complex pattern dependent on the high water level, and the outer bank is controlled by overmarch ebb tides. So I now finished, and I'm happy to have your suggestion and questions.
Wow, Marta, that was amazing. Thank you very much. Very interesting talk. So now we are open to questions. So please remember to write your questions in the chat and then be sure to send it to everyone. And also please remember to write your name and where are you watching at. So we have a couple of questions now in the chat. So the first question is from Jacob from Bangor in Wales. So what are the causes of the morphological changes at the study site? Mainly internal or external forcings? And what do these forcings tell about the wider implication of your study for this estuary and estuaries elsewhere?
Sorry,
yeah, I can repeat the first part. Yeah, I can repeat the first part and then the other part. So what are the causes of the morphological changes at the study sites? Mainly internal or external forcings?
So for sure, the tidal amplitude, the different type of tides that are reaching the area are the most important cause the morphological changes and the preservation or the erosion of these morphological changes in the study site. So they are mainly the forcing are mainly related to the type of tides that are occurring within the meander. So that there's also the peculiar flow pattern, the mutually evasive flow pattern of the ebb and flow that definitely determine the morphology of the point bar and the architecture.
Yeah.
And what does the forcing?
Yeah, and the second part of the question is, what do these forces tell about the wider implication of your study for this estuary and estuaries elsewhere?
I believe that point bars and tidal meanders developing in estuary related to hypertidal regime, so with really tidal amplitude, with really high tidal amplitude, are tidal point bar in this kind of setting can work like the one I studied. However, when the tidal amplitude is much lower, the hydrodynamic and the morphological changes really change a lot. So I believe my study is really interesting for hypertidal setting, but I believe it doesn't say a lot on I don't know, mesotidal and microtidal setting, because really the external forcing, the hydrodynamics are completely different. And furthermore, I would say also that this is really a tide-dominated environment, so there's no the influence of wave action and river is negligible. So again, when these forcing come in, the morphology and the point bar deposits will be different.
Perfect. Thank you, Jacob, for the questions. And we have a second question from Sarah Gills from New York. And she said, great talk. How do you think the morphology of a channel might influence the balance of accretion erosion experience during ebb and flood flow?
So this is really an interesting question because I think I'll try. So the elevation of the point bar itself, is it quite different? So I cannot go back because otherwise it will take too long, but the elevation of this portion of the seaward side here is much lower than the elevation of the side in here. This is related, of course, to the flood flow, and this actually allows the flood flow to cross the point bar bodies, and then with the decrease in the energy of the flood, help to deposit sediments in the apex zone and landward. So physically the morphology of the point bar changes because of this behavior.
Great, thank you. So we have another question from Maria from Svalbard, who said, thank you for the great talk. You use Lidar scanning for a lot of the data. Do you think DEMs from drones images would be sufficiently good to do the same?
So I'm not really sure about the resolution of drone. So again, I use terrestrial laser scanner, which is quite a long procedure, but it gives you in the near the scanning station, you can have something like 10 points per square centimeter. So the resolution is really, really, really higher. Of course, going far from the scanning station, the resolution gets lower, but still there are quite a lot of points in the point cloud analyzed. So I really believe that if from drone, if you can have dams with really high resolution from drones, you can do this kind of analysis, particularly for the daily time scale, because in that you have to be like you have like just a few centimeters of accretion, so you really need the high resolution. For the yearly analysis, you can actually do that the synthetic stratigraphy with a little less precision and resolution.
Yeah, thank you, Maria. Thank you, Marta, for your response. So I have a question, actually. Did you record any influence of storms in these records?
Not storms, because actually this is the site is really near the Mont-Saint-Michel Bay, and until a few years ago, there was a road coming from the land toward the Mont-Saint-Michel Bay, which actually really protect the site from storm events. And also there are sometimes tidal bores occurring here that might be more affecting than storms. But we didn't really check for the tidal bore deposits.
Okay, remember that we are still open to questions. So do you see, it's again Maria from Svalbard who asks, do you see any seasonal signatures in your record?
In the studied point bar, since we do not have a lot of tidal rhythmites, we are not able to see a seasonal signature. But there are a lot of works in the Mont-Saint-Michel Bay, mainly done by the group of Tessier, the model Tessier, which show really important seasonal signature in the upper intertidal zone. A little bit, I would say, a little bit higher than where I studied. So in salt marshes, in the really almost supratidal zone, you will have seasonal signature.
Perfect. Thank you very much. So please remember to send your questions to everyone in the chat so everyone can see your questions right there. Also, I have another question, Marta, for you. What do you think? Why nap and spring sequences are not registering all the tides that flood the area? Is it a problem of erosion?
I believe that it's more because of the energy and the possibility to deposit sediments. I mean, the tides reaching the area can be really just few centimeters above the surface, which is not able to transport and deposit sediments. So if you say that there are 22 tides in a nip spring cycle at that kind of elevation, a part of that tides will not have the energy enough to transport and deposit sediments in that portion of the bar. But, and also, of course, it sometimes can be also related to erosion when really huge tides with really high elevation, high water level arrives. They can be they can cause erosion of the already deposited tidal rhythms.
Perfect. Thank you very much, Marta. Thank you very, very much. So thank you, Marta, for your presentation. Thank you all for attending to this very interesting talk. So, and don't forget to join us next Wednesday for our third SEDS Online Great Debate entitled Autogenic Processes in Sedimentary Systems Are Just Part of the Allogenic Spectrum, in which David De Frischauer and Andres Strasser will be arguing for the motion, and Anthony Silhito and Sam Perkins will be arguing against the motion. So it's going to be a really great debate. So thank you again, Marta. Thank you all for being here, and have a nice week, and see you soon.
Bye.